Okay, hello everyone, and welcome once again to the Convex Live community call. Hope you're all doing well. So for today's topic, we have a very interesting new development in the in the world of Convex that we'd like to share and demo and discuss and talk about some of the big ideas around. But this is the Data Lattice File System. So in previous calls, we've talked a bit about the data lattice, what it is, how we're using lattice technology to create this sort of very scalable data infrastructure for sharing content of all sorts in a truly decentralized way. And the Data Lattice File System is building on top of that to create effectively a file system, just like a regular computer file system or a cloud storage file system. So we're going to be talking a little bit about what it is, how it works, and a bit of a demo of the sort of hot off the press code which is supporting this. And as always, we'll be chatting. If anyone has any questions, wants to fire a question either on the YouTube chat or join on the Discord, on the Convex Discord, then feel free to ask any questions or comment, or indeed if you're on the Discord, you can join the live chat. With me on the chat, I have Rich. Hi, Rich.
Hey, Mike, how are you?
Not too bad, not too bad. So, Rich, I was just going to ask you. You've got a bit of a background in storage, right?
I do. I actually spent 12 years as a product manager in storage for Hewlett-Packard. Everything from the desktop tape through to the enterprise. So the biggest iron that HP offered.
Awesome. So
I
we have an actual
actually,
storage expert in the room.
yeah, I was product manager on a bunch of solutions that go on top of it, like disaster recovery as well. So when the towers fell in 2001, my product was mirroring under the river from New York to New Jersey to save the financial district.
Wow, that's quite an important job to have on your hands.
Yeah, so I know quite a bit about storage.
Okay.
I probably forgot most, uh, more than what most people know.
And funny you should have mentioned Hewlett Packard. So when I was a poor student, I used to do summer jobs working as with an HP dealership, and my job was usually to go around to different customers' offices or homes and install their brand new shiny HP computers, configure the disk drive, set up all the local networks and stuff like that. So who knows? Maybe I actually installed some of your products back in the day.
Yeah, you
Um,
might have.
Great. So let's talk a bit about data lattice file system and what's different about DLFS, the file system, and the data lattice itself. So I think of this as like two levels of a stack. Yeah, the data lattice is the underlying substrate that defines the data structures and the transport, the way that data structures are transferred around, and the way that you can locate data using their hash. So it's a bit like IPFS. We have content-based addressing of data. If you've got the hash and you've got someone willing to provide you with the data that corresponds to that hash, then you can retrieve it, and then you can validate that the data is correct against that hash. So it's like immutable content of any kind of data, any kind of format, any kind of data structures. But the data lattice supports some quite advanced structures like maps, indexes, anything in JSON, all different kinds of data types. And one of the reasons that the data lattice data types are so well developed is because this is exactly the same technology that we use in Convex for the decentralized network, for replicating data across peers, for storing all the peers' data structures, for storing all the data structures that we use inside the Convex virtual machine. So these are high performance decentralized data structures. And the data lattice lets anyone use these same data structures. And the idea, of course, is that while Convex consensus creates like this sort of on-chain solution for for transactions, economic transactions particularly, that are validated amongst the peer network. There's also off-chain data, and the Data Lattice provides all the off-chain data. So you've got a lot more scalability, a lot more ability to provide large content, large files, media, videos, whatever kind of content you want is a benefit for the Data Lattice than going on-chain, which is really for you know, transactional data, stuff that you need to support an economic transaction. So the Data Lattice provides this substrate, this data substrate, but that's not enough for practical usage of storage. So particularly, like if you have a file system, you're going to want to change the file system. You're going to add new files, create files, delete files, create directories. There's a lot of changes you're going to want to make to a file system. A file system is not immutable. Yeah, it is a place that you store data and files, but that may change. What files you're actually storing or managing at any one time may change, and sometimes you want to delete old stuff. So DLFS is like a layer that sits upon the Data Lattice that says, okay, right at this point of time, this is the data that's inside this file system. It's like, we call them drives. That's inside this drive, but that might change. Yeah, so the content inside a drive might change over time. So if you like, you can think of a drive as a pointer to a snapshot of data, and that snapshot is an entire drive structure, like a disk drive or like a file system on Linux. And it's got directories, it's got regular files, it's got a few other interesting features, but it is a fully featured file system. And at any time, you can ask DLFS, well, what's the root of this file system, and what's the hash at the root of the file system? And that gives you a snapshot of the entire drive. Yeah. So at any point in time, you can say, I would like a frozen version of this drive. That's fine. You can just take the root of the drive, and that's then a snapshot, a data snapshot of that entire drive. But then you can continue changing the drive, but you can still keep the snapshot. So the snapshots can be stored on the Data Lattice. It's just a standard Data Lattice data. So slightly long-winded way of saying, but going into a bit of the technical details, but what it effectively gives is a file system that works just like DropBox, works like Google Drive, works like the file system on your laptop. So it's got a very familiar kind of mental model, although the infrastructure underneath is the Data Lattice. And that's the key innovation here. This is a decentralized file system that you can run across any arbitrary number of nodes. It can be larger than the storage on your computer. It can pull the information from the Data Lattice on demand. You can have these, you know, this very powerful decentralized system based on DLFS drives, and have everything just work underneath from the Data Lattice. So,
Mike,
did
a
that
question.
make sense, Rich, from you as a storage
Yeah,
expert?
yeah, it does. A question that'll help clarify on these snapshots. I assume we're taking a delta if we do another snapshot. Is that correct?
Correct. Yes. So this is the beauty of the Data Lattice data structures. They are all based on what's called persistent data structures, which means that if you change them, you only need to store the delta.
Right.
And this is super efficient. So if you only make one small change, add only one small new file to a directory tree, then you're only storing the new file itself and maybe a directory entry or two that has changed because of the you know, the underlying contents changing. But the rest of the files, all the big data files that you have in the same drive, they're all completely unchanged. So you don't need to store or allocate any additional space to copy those. It's just a new snapshot with a few small changes. It's very much like in advanced databases when you're doing multi-version concurrency control, and you can take a snapshot of a table at any time, and then other threads can go on changing the table, but you've got like a consistent snapshot that you can then query. It's kind of like that, yeah, and it's sort of similar kind of underlying techniques, except we can do it with anything. We can do it with any data, and we can do it with any aspect of the file system. So you can snapshot directories, you can snapshot files, you can snapshot the entire drive, yeah. So it's
this was kind of a big deal. This was kind of a big deal back in the time when they were inventing network attached storage, and NetApp could do these snapshots very efficiently. Everybody else was trying to catch up.
Yeah, yeah. I mean, I can imagine that's a major advantage if you can support it. And
yeah,
I think the thing is, though, now there's no reason not to support it. I mean, it doesn't add, on modern systems, it adds virtually imperceptible overhead to be able to do these snapshots. I mean, all the convex data structures, we snapshot the entire convex CVM every time a transaction happens. Yeah? And that's a big data structure, and we're snapshotting it maybe 1 million times a second. Yeah? It's just so cheap to be able to do these snapshots. So, you know, yes, there's a little bit of overhead, but on a modern computer, it's so small that, you know, there's no reason not to have these kind of capabilities. So
most people
from the YouTube chat: can you change a drive name? Yeah, I mean, you can kind of do what you want with drives. So one of the things that we still need to solve is how you address them. So what we'd ideally like is to have like a URI with like DLFS and then some kind of path to a drive, and that path can be sort of location independent. So wherever you are in the world, you can refer to a drive, and then you can, if you're able to access the places where it's hosted, you'll be able to modify and manage that drive. But we need an addressing scheme to do that, and that's something we haven't finalized yet. I mean, some good ideas, but hopefully it's like a URI. It'll be something like DLFS : and then some path that identifies the drive, and ideally we link that back to on-chain authentication. Yeah, so imagine if you have an identity, a DID, a decentralized ID on Convex, maybe your ID number 12357, and then that ID is what's used to authenticate your access to the drive. Yeah, so we can make use of the decentralized identity and authentication and digital signatures to do the access control on drives. But you can also run drives locally and just create them for free, and you know, do whatever you want with them. I mean, I'll do a quick demo. So storage just there's underlying storage. Yeah, so for whatever data you want to store locally, you'll need a hard disk, or you can do it in memory as well. But I suspect for most people, you'd want to use a disk-backed local replica, and then it's just regular storage cost. I mean, we use we've tested it with in-memory stores, which is one reasonable approach if you only care about doing things fast and you don't care about durability and you're just processing stuff. In-memory storage might make sense. Obviously you're limited on size on that, or you can use etch. So you can use the same etch database that Convex uses is usable for DLFS, so you can use that as a backup as well. And you know, it's kind of pluggable. We may be able to put in alternate storage providers underneath DLFS in this sort of in the future, if it makes sense. I mean, it may not always make sense, but you know, probably in memory, using etch, and maybe some kind of remote network attached version are probably the three most likely options for DLFS.
What's your question? What's your question, Riley?
Oh, I was just wondering, like, in these drives, are they able to support any file type, any file format?
Hey Riley, sorry, you're very quiet. Could you speak up or nearer the microphone?
Might just have to type it out if you can't hear me. Can you hear me?
Yeah, I can hear you. He asked, will it support any kind of file structure,
Yes.
Format.
Yeah.
file type?
Yes. Any type of file type. It is a drive. It's going to be pretty much POSIX compatible. So there's this POSIX standard which describes drives for Unix and Linux and various other systems, and we're probably going to be as close as possible to POSIX compatible. There's a few weird things in POSIX that we might not be able to support, but I think we can probably do most of it. Does that make sense, Rich, from your perspective? I mean, POSIX is probably the standard for this kind of thing.
Yeah, yeah. It gets a little hairy when you're trying to do Unix and Windows and things like on a offline drive, and that's really just the connector. If it's formatting a file system, that's a problem. Sometimes.
Yeah.
You find that like on a thumb drive too, right? Oh, it was formatted for my Windows and it didn't work on my Mac.
Yeah, there's always going to be there's problems if you move across systems. I mean, if you pick file names that are compatible with both Linux and Windows, I think DLFS will be pretty compatible with both of them. But you can obviously choose file names that don't work in one or the other. So there's plenty of fun novelties. Video files.
Yeah, that's why POSIX is a good choice. Yeah.
Question from YouTube: video file that's 1 terabyte. I mean, why not? I mean, that's absolutely fine. One of the great things about Data Lattice is that it supports lazy loading, so you don't have to load all of the data into memory at once. So if you've got a 1 terabyte video file, it can load it in chunks as you're reading it, and then you can stream it or do whatever you want and process it, and then write it back out again. And again, you're just doing it in chunks, so you're never actually going to have to load the whole file into memory at once, which is really important. And again, one of the reasons we can support this is because we designed Convex to support very large transaction histories, very large belief data structures, which might be larger than the memory of a peer. So we need to have this ability to stream in data dynamically on demand, and not blow main memory. So exactly. Can you email me a file and have you load it onto DLFS? Yeah, I mean I could. Yeah, I'm about to do a demo. Let me do a quick demo, and if you want to send me something to play with, then do it, or send it on the Discord or something. Let me just move to this mode, and we can do a quick demo. So I've got some little files ready to play with the browser. So this is the new DLFS browser app. It's part of the Convex desktop sort of bundle, and I've just set up a little DLFS drive for sort of testing purposes. So you can see that it's a bit like a regular file browser. I've got a root drive, DLFS root. I've got a few different directories. Sort of this is from an AI, some AI directories that you might have. You've got some models, you've got some training data, input data, etc. Just for testing. You'll see that there's a couple of things at the bottom. There's a root hash. So that is the hash which is the root of the drive. So if you wanted to take a snapshot of the entire drive, that is the hash of that snapshot that you could use with the Data Lattice to see the entire snapshot. And each individual node, each directory or each file also has a hash. So if you wanted to snapshot one of those, you could take a snapshot of those at any point. Now, if you want to put a file on the Data Lattice, let's just take this. I've got a Convex logo. I'll just drag it in here, and you can see there's now a Convex logo in the root file structure. And if I click on that, you can see a bit of extra information about it. So it's a logo, PNG. It's 13K of size. This is the data hash. So if you were to take the actual blob binary data of that file, that's the hash that lets you get to that data. And then this node hash, it's the same as this node hash here. It's the node that that if you wanted to take a snapshot of the file and its metadata, so basically the node in the directory tree, then that would be the hash that would let you have that as a snapshot. And there's a bit of metadata, so like when it was modified, it's all done with Unix timestamps, but you can display it in your friendly local time as you wish. So that's a file. The directories are kind of similar. If I click on a directory, it'll say, well, this one's a directory. It's got 0 entries inside it. It also has a node hash. So if you wanted to snapshot that, you've got the node hash. And it also has metadata about file updates and stuff like this. So as you can see, this is pretty much, and if I want to delete the file, I can just do delete. It's gone. Yeah. So it's just like a standard.
Wow,
drive.
The coolest thing about that was drag and drop.
A normal file system, Windows Explorer. We haven't yet got all the features here of a sort of a full file explorer, but we'll be able to add them over the coming days and weeks as we sort of flesh some of this out. But it's functional already. Yeah.
The coolest thing about that, Mike, was the drag and drop.
Yeah, drag and drop is nice. Yeah, it's kind of fun. But now we've got to do something cool, really cool. So I talked about how drives can be snapshotted at any point. Well, there's a snapshot. So I've just cloned that entire drive. Yeah, so the second window is actually a separate drive, but with a snapshot that's exactly the same. And if you notice, you'll see that the root hash and the node hash are exactly the same. These are two snapshots that are precisely identical. Let's say, however, I decide I want to change this one, upload a file back into this one, and I've now got the Convex logo in this. You can see, hang on a sec, the root hash here and the root hash here are different. These are now not identical snapshots. These are two different copies of clones of a file system. And if likewise on this one, I can put this API demo text. There you are, put that on there, and that one's now changed. So that's, again, it's got a different root hash and a different node hash of this. So API demo is just another small file, like 670 bytes or something. So I've now got two clones of the drive that originally started from the same snapshot, but have now diverged because I put different files in each one. Now, obviously this is going to be a problem if you're running in a sort of decentralized operation. So what we have in DLFS is this very powerful replication capability where it will just sync from the other drives whenever you want. Yeah. Now you could have this rolling, continuously syncing, but I've turned that off at the moment just so I can demo what happens. So if I decide on this, my new drive, I want to sync back up with the original, I'll just click sync, and you see I've now got the Convex logo file that came across from the original drive. So it's done the replication, it's realized, hang on, the hashes are different. It's compared the trees of the directories in the two different snapshots and says, well, what's changed? And it's found, oh, you've got a new entry, directory entry. This is a new Convex logo. This is a new file. I haven't got this file. So then it pulls that file from the source and includes it in the replica. So now the replica has the changes from this file. But of course you can do it both ways. So if I go back to this file, this drive, press sync, you'll see I now have the API demo and the Convex logo are now both back in this directory. So it's synced back into this drive. So now the two drives have the same file contents. Yeah.
Right.
And there is one slight difference. They've got a different root hash and a different node hash. And you might go, well, why is that? Yeah. And it's because the time at which the update happened was a little bit different. So the time of directory update was different. Yeah, the last modified time of this, it was a more recent update. However, I think if I sync it again, yeah, if I sync it again, each time I'm going to get a slightly different update time. So, but in fact, the contents of both of those are exactly identical.
Now that's with you doing a manual sync, but if you did an automatic sync, would the hashes all come out even?
So in fact, yeah. So I mean, the hashes should come out even if you don't update the directory times.
Okay.
If you update the directory times, then they will come out different.
And even if it's automatic, it'll be, like milliseconds, so it would always be different.
It might be in the same millisecond. It probably is less than a millisecond on a local copy, but yeah. So probably we might want to take a look at that actually and say like suppress updating directory times if the contents don't change.
Yeah.
So I mean that's an interesting question. Do people want it to converge to the last unchanged directory, I guess.
Yeah. Well, I know we have that capability in our merge function on the compute side.
It's just doing a convex style merge anyway. Yeah. So yeah, we should probably figure out this is probably to do with the logic, in fact. So if you're merging and you update something that was previously updated, but your change doesn't actually change the content, you probably don't want to update the modified time. So yeah, that's worth looking at. Interesting one. Because yes, it would be nice if they converged to exactly the same snapshot and after syncing back and forth 2 or 3 times, and that would help give people assurance that the replication had ended up in a sort of stable point.
Right.
But yeah, I mean that's the core. That's DLFS. That is a complete file system. POSIX, mostly POSIX compatible, I would say. It's probably not ticked all of the boxes of POSIX yet, but it's mostly POSIX compatible, and it supports full replication, and it supports all the decentralized structures on the data lattice. So you'll be able to host these for yourself, for other people. You'll be able to have a sort of peer-to-peer setup where you share drives, like in a company, and you replicate to make sure everything stays up to date. So I'm kind of thinking that, with a little bit more development, we should probably dog food this and use it as a replacement for, Google Drive or Dropbox or this among the sort of Convex core team, because it's a good way to be actively using the data lattice and actively testing it, and actively making sure that we're building something that's broadly useful. And then this, I think, becomes a product. Yeah, this the Data Lattice File System becomes like a decentralized Dropbox, like IPFS. I describe it as IPFS meets Dropbox meets BitTorrent.
Mike, can you save the photo? I put it in main chat.
Hey, sorry, Riley, I think you're trying to say something, but you're really, really quiet. Could you... Did you hear that, Rich?
He said, "Save. Can you save the file he put in meme chat?"
The file in meme chat. 1 second. You've not sent me anything dodgy, have you, Riley? Okay. Convex wallpaper DLFS demo. Yep, got it. Let's put it in here. There you are. There's Convex wallpaper DLFS demo. 62K. Yep, nice. Worked. Where's that input? Sync. There you are. Synced across the two. Yep, so that works. Absolutely. So any file you want to put in there, it literally doesn't care about file content at the types at the moment. It considers everything a binary blob with a name, and that's pretty much it.
So assume you have a whole bunch of peers that decide that they want to host a storage node.
Yep.
And these two things here represent separate nodes. How do we think about how they'll merge and keep the same information, because of the thing you mentioned about BitTorrent and being able to get stuff from a BitTorrent?
Right. So that's a really good question. So the data lattice data structures are basically big Merkle trees. Yeah. With potentially lots of nodes, potentially larger than memory, potentially decentralized and distributed across multiple places. But let's forget about that complexity. They're essentially Merkle trees, and they're very efficient Merkle trees. And because they're very efficient, it's very easy to scan one of these things and say, well, have I got the whole Merkle tree? Do I have this entire thing stored in my own local storage? Yes or no? And if you haven't got it stored, then you can say, well, what are the bits I'm missing? Because you've got all the hashes of up the Merkle tree. So if there's one of these hashes and you haven't got the data that hash points to, you're missing a chunk from this tree. And then you can go and get that chunk from someone else. Yeah. So that's why I say it meets BitTorrent. Yeah. Scanning one of these data lattice structures will give you a list of missing chunks, which may be empty if you've got the whole thing. And then you can, from anyone who's willing to serve up the chunks to you, you can then just download those from other peers, from backup storage, from your caching node, from a CDN, whatever. Yeah. And of course, it's all hashed, so no one can cheat. Yeah, if they give you some bad data, it's not going to match, and you'll know that you were defrauded. So it's a very powerful way of being able to distribute data, and it works effectively like BitTorrent. Yeah, BitTorrent keeps a map of which chunks of a file it is missing, and it then collaborates with other nodes in what they call a swarm to go and pull down and download those missing chunks. And there's a bit of the BitTorrent has some protocol stuff to help, like manage incentives, help penalize people who are cheating, etc., etc. But that's essentially how it works. It goes and just collects chunks from a swarm. What I think is a little bit different with the data lattice is, like, in BitTorrent, your swarm is around a particular file. Yeah, so you create a swarm that's serving up this particular content. So BitTorrent is kind of designed for big chunky files where you want to download it fast, and there may be hundreds of people around the world also trying to download the same thing fast at the same time. And the swarm's speed comes from the fact that they can all collaborate and they can all share bandwidth with each other, etc., etc. So BitTorrent is very much designed around sharing a single file in a torrent, whereas the data lattice is more about sharing arbitrary data. Yeah, so you can ask for quite small pieces of data at quite a granular level. Yeah, so this file, for example, is probably much smaller than you would have in a typical torrent, yeah. But it itself, you could ask for like the first chunk of that file, yeah, down to quite a
Right.
low level on the sort of the Merkle tree. So um, and the connections on the data lattice, they're not for a specific file, they're for, you know, well, whatever content is being hosted by that data lattice node. So as long as you're able to serve up that particular file, then you might get a request for that file, you might get a request for a different file, you might get a request for the root snapshot of a whole drive. Yeah, it all works in exactly the same way. And so it's more fine grained, I would say, than BitTorrent in terms of design, and it's designed for distributing arbitrary data rather than, you know, having a small, rather than a small number of big files, which I think BitTorrent is well designed for. The data lattice is for a very large number of Merkle tree nodes. Yeah, so if you think of a big store of Merkle tree nodes, that's probably
Right.
probably a good analogy. So, but a lot of them, yeah, sort of, you know, this could be millions, could be billions, and each of those nodes is probably, you know, a couple of K in size. Yeah, not particularly large. So the data lattice supports these much more fine-grained data structures directly.
So most people are pretty familiar with Dropbox and trying to send a large file, and sending a large file is a pain. Sometimes, you know, you can't put it in email, you can't do this or that, and so you have to use one of these tools. How could we be using Data Lattice for that kind of file transfer protocol?
So I think it's a good question. So I think what we probably want is a link. Yeah. So you can basically create a link that you can send to people
Mm-hmm.
to a file, and that link would be to one of your own nodes, or maybe a public node, or maybe a node that you've, you know, paid a service fee to host things for you, and that would effectively be a data lattice link. So they can do one of two things. They could put it in their data lattice browser and browse the file or the directory, whatever you'd sent to them, or they could use a HTTP proxy. So if there's an HTTP proxy that you can just put in the link, it'll be able to resolve that file for you, and, you know, assuming you've got access rights, serve that up, and then you don't need to have a data lattice browser. Yeah, you don't need any special software.
Yeah.
You can use a regular web browser to
So much like Google Drive.
Yeah, pretty much. So basically, we could have a proxy hosted version of DLFS that anyone could run. Yeah, and I think the difference between Google Drive is obviously a centralized system. You know,
Right.
you can't host your own Google Drive infrastructure. Um, Whereas with this, anyone could have a data lattice DLFS host and just say, yes, I'd like an HTTP page, and then you've got an HTTP proxy. You can put it up on your website, or you can, you know, otherwise give people access to that proxy, and then anyone can download from it. And it's kind of like IPFS in the sense that, because everything's content addressable, if someone else has a copy of the same data, it's just as good getting it from them as it is from yourself. Yeah, because it's the same data. You can
Mm-hmm.
prove it's the same data because it's got the same hash. So as long as you've got enough replicas around, you could, and, you know, some of them could be public replicas, some of them could be hosted ones. You could always, you know, you can always guarantee being able to regenerate your file, like in case of disaster recovery or stuff like that. So it's kind of flexible in that sense. I think that the thing that gets maybe interesting, obviously some of these drives you're going to want to keep private. Yeah, you're not going to want to give the whole world access. So if you were doing a hosting provider, you would need to have, you know, some kind of policies and access controls on that.
Right.
I'm kind of hoping we can just use the standard digital signatures, ED25519 signatures that Convex uses, and then it's going to be pretty easy. Yeah, you authenticate yourself by, you know, signing requests, and those requests then get honoured if they're consistent with what you're asking for. Interestingly, there is an option for micropayments here using Convex, because you could send a transaction, say, look, here's my payment, and the host can say, okay, here's a payment that's going to pay me for accessing this file. I'm just going to submit that transaction on the user's behalf and then serve them the file and get paid whatever amounts in that transaction. So that's an interesting option. So you could do like micropayments on the network related to providing files. So it creates a few different potential business models for DLFS hosts. And of course, if you're going to host a lot of data, you know, you do need a business model. You know, the storage and bandwidth isn't free. So,
right.
You know, some people may operate public things in the public interest, but you know, a lot of the infrastructure and storage is not going to be for free, and people are going to want to keep it private and secure and all of this kind of thing. So, you know, I think the important is
I could see, yeah, I could see where folks like creators would want to give access only to their paying clients, etc., to certain bits of data.
Yeah, and this is the, I mean, part of the power of the data lattice is flexibility. Yeah, you know, anything you can do with a forest of Merkle trees, you can do with the data lattice. So if you want to provide strong authentication against the roots of some of those trees, then that's totally fine. But yeah, I mean, but that's going to be I think a choice for users and for hosting providers, exactly how they want to set some of that up. So currently it's designed more as like a public Dropbox. So you know, we're not putting any particular strong authentication on it, apart from you control the routes of your drives. Yeah, so no one else can come in and change your route of your drive. So if you want to replicate from some other public drive, you can, but you know, you're still in control of whether stuff gets replicated into your drive. It's always kind of like on a pull model, the replication. And if you want to push to somewhere else, then that place needs to authenticate that you're actually, you know, legit, and that you can push to it. So in a way, it's a bit like Git. So Git version control. Yeah, anyone can pull from an open source repository, but they can't push. They have to, you know, request that the container pulls from them.
This is fairly new, so I'm not sure if we've got it available on testnet yet. Can somebody, you know, and then how does somebody create one of these drives, and how do they mount one of these drives?
Currently it is only available in the Convex desktop app. Yeah, if you want to play with it, and it's also in the Convex, you know, source code if you want to access it programmatically. Now, in order to make it mountable, that's a really good question. We could make these things mountable. The problem with making these things mountable, i.e., you can like see them with your regular Windows Explorer or your regular, you know, Unix file system. You could mount them as a sort of, you know, a path in a Unix file system. That's definitely possible. The only challenge is that's very operating specific, system specific, how that works. So you would need to install software for that operating system that allows you to mount the DLFS file system. So it's kind of, we'd have to write a file system driver for each operating system that we wanting to support mounting DLFS drives. So not impossible, but it's an extra chunk of development work, which you know, probably if you wanted to create a DropBox competitor, you'd want to do that.
Right.
But it's not yet in our sort of core app. It's a bit more of a chunky integration, and it's operating system specific. Yeah, the beauty about this is it's totally cross-platform, and you know, it's just it would work on the Mac the same as on Windows. But when you start linking up to the operating system file system calls, it gets a little bit more
right.
Involved from an infrastructure side, which is fine. It's doable. I mean, plenty of people do it, but it's just a little extra piece of development we probably won't do until we really focus on the productizing this for Dropbox.
So could you show us how somebody could use the desktop app and get to a file system? Is that possible at this?
Let me just double check that that's working. One sec.
So they would just use that browser app that we have. Is that what you're thinking?
Yeah.
Yeah, that. Yeah. And then you'd make it a part of that.
Yeah. I'm not sure. I've not got the launcher. I've not even got the launcher hooked up yet. This is new stuff. So yes, there will be a button on there for DLFS drive or something like that. That would basically bring you into this browser, and you know, I think and there'll be a bunch of other options. So the kind of things that I think we want to do in the sort of the next phase are a bit more linking to the Convex network. So, for example, I mentioned decentralized ID being used for DLFS permissions. I think is really good idea, because then you've got like a public version of truth and authenticity that you can validate against. So you've got the root of trust. That will probably be the preferred model for identity on these systems. I mean, obviously you can create a local one with full permissions of whatever you want, but if you want to share these things publicly then and have like public access to drives or team access to drives, this kind of thing, then you're going to want identity proofs, and probably the decentralized ID on Convex is the best way of doing that. So that's a future development. As you say, allowing native mounting for different operating systems would be a future development, and just improving the browser, improving some of the sort of the tools that work with it. That's definitely an interesting project.
So it opens up a whole bunch of opportunities for community contributors.
Yeah, I mean, this is I've honestly had so much fun hacking on this. And if I sort of, there's something very beautiful about when you're building something on top of a very powerful substrate, and it's so easy. Yeah. Building a file system would normally be considered an insane project. This got written over a weekend. Yeah.
That's awesome.
Not because I'm claiming to be that great a genius or anything, but because all of the data structures, all of the capabilities of the data lattice were already there. So it was simply building a user interface on top of it and a little bit of logic for disk syncing. Yeah.
That's crazy.
And the file system structure and syncing the file system structure. So the actual amount of work to get DLFS to this state is probably less than a week, and that's because Convex provides all the data structures, everything we needed to be able to do all of the heavy lifting on the data, the Merkle trees, all of that is already there. So it's just plug and play at that point.
Yeah, that should give people who want to build on top of Convex some confidence that they can get things done quickly.
Oh yeah, I mean it's just so what a. I'm just going to see if I can find something. 1 second. I just wanted to give a little bit of a example of some of the.
Could anybody hear me?
Yeah, we hear you,
Yes,
Quarkside. What's
you're
up?
quite quiet. You're quite quiet. What are you saying there?
I asked a question, but it hasn't been answered, right? And it was just about a use case.
Sorry, what was the question?
Oh, there's a bunch of questions in YouTube.
Oh, sorry.
Would you put an AI model on?
Yes. So, can you put an AI model on? Absolutely. So, any kind of file works totally fine. Let me see if I have an actual big AI model. 1 second. See. See if I can find an actual big model. Okay, this is a 7 gigabyte model. Stable diffusion base, safe tensors. I'm probably going to crash this. I've really not tried this yet. But this is a 7 gigabyte model. This is relatively chunky AI model for image generation by Stable Diffusion. And I don't know how long it's going to take. I don't have a progress bar. Let's see if it gets there. If it gets there, I'll be pretty happy because it's really not been tested chunking anything as big as that at DLFS. Kind of annoying it hasn't got a progress bar, but anyway, while that's going, other questions?
There was a progress bar at the beginning. It disappeared.
Oh, it's there. Ah, okay. Yeah, okay. I got a bug. I've got an overflow or something. I wonder if that's a Windows problem. Yeah, that's overflowed the size of a file on Windows, or the default size of a file on Windows. Okay, I'll have to check that, but maybe there's a smaller one. I think if I stay less than a gigabyte, it's probably fine. Do I have a small model? Videos. Maybe I've got one of the YouTube videos. 1 sec. DropBox.
Well, they bring up a really good point about decentralized AI, and it seems like this is very well suited for decentralized AI solutions,
Yeah.
and that's a big opportunity.
Yeah, so I mean, the kind of things that I'm thinking people sharing is people like collaborating on AI models, yeah, and replicating training data, and it comes back to the authenticity and the provenance. Yeah, you've got these hashes so that you can guarantee that you've got exactly the same data and exactly the same model as someone else running similar tasks. And if you're looking at data sets, if you've got IP and intellectual property and you want to validate the contents of your drive, which is containing your training data, so that you can manage IP claims. Again, these Merkle tree snapshots let you very clearly define the provenance of what you used, how you used it, when, all of these kind of things. So you know, I think it's more than just a file system. It's a file system with very strong integrity and authenticity capabilities.
Yeah, even your file structure there, you know, when you started, you mentioned those things were all things that are needed in an AI modeling,
Yeah.
the directory structure.
Yeah, indeed. So let me just. I've got a couple of videos from some of our chats. 1 second. There's a video. How big is that? Okay, that's a few megabytes. It's not particularly big, but I mean that's a few megabytes is instant. Yeah. I think you know, if I can find a big one. Properties. Why do I have all of these small files?
There's a new camera out from FreeFly. It's the Amber S2.5K, and it'll do like 75 terabytes of data on the one card. I'm like, that's crazy.
That is really crazy. Yeah. Yeah, I mean, I do think a multi-gigabyte file would be pretty much instant still. You know, a couple of seconds or something. You would obviously have to load to copy all the data, but I mean, it should be seconds. I'd have thought. I just can't find one that's not going to blow the copy limit.
Yeah. So if you just had a plain NAS drive connected and it didn't have the like a Windows file system on it, it probably would work fine, huh?
Yeah. I need to check. I need to check why that was failing. But I know there's some like size limits on some of these transfers on Windows. So that probably just need to double check that I'm using the right API or something. I see another question. I think this is a fantastic question. Presume you can prevent syncs for audit? Absolutely. Yeah. So first of all, when you sync is always a decision of the user who is syncing. Yeah. So a decision to pull, and they can pull continuously if they want, but you know, it's always in the control of the user. So back to self-sovereign, decentralized principles, it should be the user who controls when their data gets updated. So sync is in the control of the user. And secondly, for audit, in fact, you would audit a snapshot. Yeah, you would say, okay, I'm taking a snapshot at this particular time, and I'm keeping that snapshot for audit, and then I'm continuing any future changes are then separate from the snapshot. And you know, as we've commented before, that's super efficient because of the way that the data structures work. So yes, you then just run your audit on your snapshot. You can say exactly what the hash of that snapshot is and refer back to that. But great question. Yeah, exactly. Snapshotting is not only useful for, you know, drive consistency and stuff like that, but it's also very important for audit. Being able to like freeze the contents of the drive and say I'm going to keep this copy. And you know, that's what's happening every time I do. So every time I clone, oops, there you are, clone. Every time I clone the drive, I have got effectively a snapshot. So this clone is not going to change until I actually actively try and sync it up. So you can have as many of these as one if I sync that. Oh, it's not liking syncing now. Yeah. I think I've broken sync by trying to include a file that's too big. Ah well, the joys of doing live demos, eh? But at least I found the bug, and that means it'll be very soon fixed. Anyway,
yeah, and if you fix it, you might get some Convex coins.
Yeah, that'd be nice.
Good stuff, Mike.
Okay, well,
if you were to sum this all up in because you got a minute.
Oh dear, that's really challenging. Well, look, okay, so we have built a new file system, DLFS. It is a mostly POSIX compatible file system that I guess merges the advantages of BitTorrent, DropBox, and IPFS, giving a fully decentralized way of sharing and distributing files, but in a tool and in a form that is very familiar to users, like a traditional file system, like a Dropbox, like a directory structure on your disk. So we make it very convenient for regular users and businesses to take advantage of the power of the data lattice with a file system interface. So how's that?
That's great. Thanks.
Okay, well, great to see
awesome.
you all. Thanks for all the great questions and discussions and indeed ideas, and thanks for helping to find a live bug. So that'll be fixed for next time.
All right, cheers.
All right, take care. Bye for now.